Hi everyone, hope you hear me well. In case you do, hello. So you do hear me, right?
Yeah, everything's all right.
Yeah, that's cool. I guess we can begin then and embark on a quite difficult yet ambitious journey of uncovering the basic stuff that that you will need for successfully acquiring the machine learning mastery you seek for. Okay, you see my screen? See the presentation?
Yeah.
Okay. So let us begin with a quick but insightful introduction. What we'll be doing for the following 8 weeks or so, we will be talking about math and in particular math applied to machine learning, artificial intelligence, and all that data analysis and all that good stuff. Essentially, we will be talking about linear algebra. We will cover the core objects and structures used in it. And we will touch on a bit of analytic geometry, but well, sometimes it's called analytic geometry, sometimes it is called a part of linear algebra. What matters is that we will talk about projections, orthogonal, normals, and planes, and hyperplanes, in particular. That will be for today. But generally, we can adopt the view that machine learning, as any practical field, is based on some pillars, and those pillars would be, roughly speaking, linear algebra, vector calculus, and some sort of optimization disciplines, and theory of probability. Well, broadly speaking, anything practically useful that uses any math is based on some sort of linear algebra and calculus. And speaking even more broadly, we can say that calculus itself is nothing but applied linear algebra. And the goal of calculus is to tell us when we can apply the instruments of linear algebra and locally linearize something, because lines and linear objects are pretty cool and simple. And when we encounter something that is not as simple and cool, we can approximate it with any degree of precision with something more, more nice to handle, in case we can do that. Or we can pretend, at least. So, in this course, we'll be talking about, again, linear algebra, calculus, and some basic optimization techniques, and what is assumed when we speak about students, that you have some knowledge of math, so you can expand terms, add something, perhaps even multiply, and you know some Python. Python will not be needed for the lectures, it will be needed for your practical assignments and seminars, but well, you still gotta know it at least to complete the assignments. What will make this course useful for and special for us all, except for the special time we spend together, given that it will never return. This course will include pre-made animations, because anything is better when you can, well, see the animation and how it moves in all its glory and dynamics. It will include some examples and links to GeoGebra, because, well, you can, when you play with examples, it's far easier to internalize the stuff. Perhaps it will include sometimes links to handy calculators to calculate everything. Obviously, it is much better to solve everything by hand, but to be honest, people rarely do that nowadays. And well, at least if you do that in calculator, well, at least you've done something. And occasionally we'll throw in some links to YouTube, because the mathematic community on YouTube is awesome. And during, well, the recent 10 to 15 years, we have acquired a lot of great videos, which will help us understand stuff way better and in a more intuitive way. And that's what's needed. Having said that, what you should expect when it comes to, well, nitty-gritty details of the course. We'll try to keep the engineering approach going, which means we will not dive in pure math too much. We will be just talking about stuff and how to apply the stuff, not where it comes from, not how it is derived, no, not how it is related to some more abstract algebraic stuff, but not saying way more than we'll need to pass the course. So we'll be rich with practical examples. We'll try to keep our definitions clear and tidy. And sadly, for those of you who enjoy coordinate-free approach, we will be using coordinates because coordinates are needed whenever we want to calculate something and get a numerical answer. Since machine learning is an engineering discipline, one might expect then that we would need to calculate stuff. So we will need coordinates, which makes everything way more messier, but applicable to everyday tasks. And what not to expect, there will be no detailed introductions except for this one, and I hope that I'm not overstaying my welcome. There will be no elaborated proofs. Well, to tell you the truth, there will be hardly any proofs at all. Otherwise, our journey would take far longer than 8 weeks. There will be almost no step-by-step derivations, and we will not entertain ourselves with the stories of the old ways and how great mathematicians arrived at the concepts, structures, and theorems that we are going to use. But I suggest we'll find other ways to entertain ourselves. So in case if you have any questions, you can ask them on the go, or you can wait till the end of the lecture if, well, the question is more general and ask them, well, using your voice or using chat messages. And I hope we will be added to some chat in Telegram where you can ask questions, well, there on your free time whenever you feel like it. Okay, does anyone have any questions related to what I have just said in my introduction before we begin? Oh, okay. I hope that means that everything is very clear to everyone. So let us begin with the basics of linear algebra. Thinking like an engineer, we have to ask ourselves, so, okay, what are the objects that we will have to deal with? And to begin with, we will be dealing with numbers, and which will be notated by this really looking R letter, which that means real numbers, but we will call them scalars to sound fancy. Why? Because when we multiply some object by a number, it scales the object, right? It makes it either bigger, makes it smaller, or it flips the direction. So that's why a simple number is called a scalar. And here, well, it is a Greek letter alpha that indicates that alpha belongs to R. So alpha is a number and a scalar. For example, -2 is a scalar. What is a vector? Well, speaking about notation, a vector is a column or a row, or otherwise it is somehow organized sequence of numbers, which we will call, or scalars, which we will call entries or coordinates, right? So we have a vector with n entries, and here is a vector with 3 entries, 5 entries, and all that. For the time being, when we have a vector that has 3 coordinates or entries, we'll say that it belongs to R3 space. And what is that? We'll talk about that in a minute. If it has 5 coordinates, we'll say, okay, it belongs to R5, etc. Well, generally we can replace R with any number field, and but in practice, usually it is if it is replaced, it is replaced only with complex numbers, but complex numbers will not appear in our course, maybe in the end, and only for a brief moment. Other thing important to notice is that a vector is an object that is in some way does not depend on its coordinates. What I mean is that in nature, in stuff, in science, in engineering, we'd like to talk about intrinsic qualities and objects that possess intrinsic qualities that do not change depending on the circumstances. For example, if you take a ball, or you take, I don't know, a mug, a coffee mug, and move it around the space, you might hope that its dimensions do not change, right? Its mass does not change, and all the stuff like that. Or if you look at some coffee shop from your window when you're sitting at home, and you describe the shop using your local coordinates, meaning implying you're an observer, and your friend is walking outside near the shop, and he describes the shop using his point of view, his system of coordinates, implying he is the center, he is an observer. We would like to hope that the shop does not change its intrinsic qualities, no matter what reference points or what coordinate systems we use to describe it, right? So vector is the same in that manner, which means we care about some intrinsic properties which do not care about coordinates. So we can write a vector in coordinates. Well, not there are many ways to do it, so any representation is not unique. That will be very important later when we'll be talking about changing the basis and decompositions. Another important object, which for now will be a simple rectangular table, is a matrix. And it's called a matrix M times N, meaning it has M rows, first row, second row, mth row, and then columns, first column, second column, nth column. And here we write that it belongs to the space M R to the power M times N, which means rectangular matrices with M rows and N columns. For example, this square matrix belongs to R2 times 2. This rectangular matrix belongs to the space R times 2 times 3, because it has 2 rows, 3 columns. Okay? Okay. So for now, let's focus on vectors. Again, so what is a vector? From an engineering point of view, we might say that it is something that we can describe by an ordered set of numbers. Usually, we try, whenever possible, to write this set of numbers as a column, but sometimes we will use rows instead, and some authors will generally prefer to use rows. It does not really matter. So we can, when we speak about a vector 1, comma 2, we can imagine something like a point on a plane, which has simple Cartesian coordinates 1 and 2. 1 for x coordinate and 2 for y coordinate, right? Another approach, we can say that a vector is a weird object that has two key characteristics. First, it has some length. Sometimes it's called a norm or even modulus, and it has a direction, so it points somewhere, right? So this directed arrow is a vector. And usually, and especially in our course, all arrows will begin at 0. So they all start from the origin, from the special place on the coordinate plane or in vector space, 0. And that is the origin. That is a crucial assumption for all the other definitions to work properly. Okay, but vectors are mere separate objects, and they would not be as much a matter of interest to us if they would not belong to some other cool structure, which is, of course, vector space. So what is a vector space? First of all, it is a set of vectors, right? And we say that vector space is some set V over R or any other number field but it's not a set. It's just a set. It is a set that is equipped with two operations. First operation, we call it, well, adding together, summing vectors, vector addition, right? What does it do? It takes a pair of vectors, so it takes two vectors and outputs a third vector, like with numbers. Well, to add two numbers, you take the first number, you take the second number, you add them together, and what you get as a result, you get a third number. So technically, you can say that you take an ordered pair of numbers as your input, and you get the result as an output. Well, if the addition is commutative, so it doesn't really matter if your pair is an ordered pair or not. Second operation is called multiplication, but it is a scalar multiplication. Why? Because it takes a scalar and a vector and returns a scaled vector, right? So it is an ordered pair of elements. Is that clear so far? Sometimes I'll use some pauses.
Yes, all good, all good.
All right. Being more formal and math friendly, we say that vector space is a stuff that consists of objects we call vectors. And what can we do with vectors? We can add them together and, well, get another vector. So this set, this vector space, we can say that it's closed under addition, which means that we can add any two vectors and get another vector which belongs to the set, right? And, well, we can scale all the vectors using scalars from our underline number field. But for our use, it will be real numbers. Okay, and it satisfies some properties. The addition is associative, it's commutative, there exists identity element for addition, basically zero vector. If you add 0 to something, nothing changes. That is why it is a identity or neutral element. It has the same for scalar multiplication, which is 1. It has inverse elements for additions. So for like with integers, right? If we take any integer, for example, 5, there is an inverse element minus 5. If we add them together, we get 0, which is an identity element or neutral element. And we can distribute just like we do with the numbers, right? So whenever everything listed here is satisfied, we are dealing with a vector space, and it does not have to be the usual image, a mental picture of a vector space we have. Like, it should not be just arrows. It can be anything that obeys those properties, obeys those laws, can be called a vector space. And, well, talking a bit ahead of ourselves, when we have something that looks like a vector space, we can say that it might be isomorphic to some interesting or not so interesting vector space, which means we can transfer from our structure to vector space, do all the operations there, and go back, because those structures are essentially the same, in case there are clearly defined rules for going from one structure to another and coming back. Okay, so we said that there is something that we call vector addition, but what it is in technical terms. Suppose we have two vectors, vector x and vector y, right? Which importantly belong to the same vector space Rn, right? They have the same dimension. How to add them? We do that entry-wise or coordinate-wise. Basically, we add the first coordinates, we add the second coordinates, and all that. When we want to multiply by a scalar, what do? We multiply every coordinate by the scalar. When we define the operations this way, we find that all the listed properties are necessarily satisfied. Again, when it is, I assume that it is an important moment to clarify and meditate on, we just make up something and call that addition, right? In some way, it resembles a usual addition we have seen, well, in real numbers or in natural numbers, but it's just a man-made construct. We just define the operation in that way for it to satisfy our previously listed axioms and properties, right? We can come up with some other way to add something and call that addition. As long as it satisfies the properties we have listed, we're good. So, for example, we have these two vectors, how to add them. First, how to multiply the first vector by a scalar. We multiply every coordinate by the same scalar. 10 times 1 is 10, 10 times 0 is 0, 10 times 1 is again 10, right? Very cool. So how to add them? 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 2. Okay? Doesn't seem so scary. For example, one moment, I have some messages in the chat. Okay. Okay, I guess you should ask that the organizer for manager for that. We'll come back to that in the end. But for now, let us stick to our lecture. Okay, like most things in math, this has geometrical interpretations. What are those? We can, again, when we talk about vectors, we can picture a directed arrow that starts from the origin and lands somewhere at some point, and this point is described by the set of coordinates. We can scale it, right? For example, 2 times a, we just multiply every coordinate by 2, or we can scale it by the negative scalar, which is less than 1. So it will shrink our vector, and minus means it will change, flip the direction. But all those vectors will stay on the same line that is drawn through the initial vector, right? So when we need to add two vectors, what do we get? We can use so-called either triangle rule, because we imagine that there is a triangle here, or more sophisticatedly called parallelogram rule. We can draw this figure, right, and use this diagonal. So geometrically, we can imagine that this red vector moves here, and the final place, the final point where it points is, well, the coordinates of our resultant vector. So to make it a bit more dynamic, everything works coordinate-wise or entry-wise, right? We can visualize it by just moving one vector to other place. Well, this is so-called parallelogram rule or triangle rule, depending on how you like to call that, and which figure, which shape you'd like to imagine. It works the same in any dimension, on the plane, in the space R3, or any other Rn space you may imagine, right? So nothing fancy here. When it comes to subtraction, it also works coordinate-wise. So difference between two vectors shows you how to get from the second vector to first, right? So what path we have to trace, how we have to move to get from W to U, right? It is this path. It works both in any number of dimensions. Okay. And well, basically, vector subtraction is like addition, but you add something negative, right? So it's all can be notated as addition. And scaling or multiplication by a scalar, it just scales the vector, right? And the resultant vector will necessarily lie on the line of the initial vector. In any dimensions, it still looks the same. Okay. So to sum up, here is how we add vectors. Here is how we subtract vectors, well, which is basically the same as adding something negative. And that is how we multiply by scalar or scale, just simply vectors. Okay, that is clear. To make sure that everything is really...
Hi,
Yeah.
hi, sorry. Hi, sorry. Actually, thank you, Daniel. I have one question actually. So all these operations we can perform in the 2D and as also in the 3D because in the examples you shown, those are very nice actually. So these operations are the same in the 2D space and in the 3D space as well, right? For example, the
Yes,
right side is the 3D, the
right.
right side is a 3D example and the left side
Yeah.
is a 2D example. Okay, great. Thank you.
Moreover, to make sure that no one gets lost along the way, as I've told, I'll provide you with links for GeoGebra. And just as one example, what here you can see there are some Russian words. I hope they do not scare you. I'll replace them with English. So, for example, if you have two vectors, v and u, right, we can manipulate them, and the resulting purple vector is, well, it's the result. It is their sum, right? So no matter how we manipulate them, we see how it changes. And if we'd like to subtract them...
We don't see it, or at least I don't see it. I see the presentation.
One moment.
During the difference.
Perhaps I have shared not my... Okay. No, let me share the screen. Okay. Now you see that?
Yeah.
Yeah, okay. I have shared not the entire screen. Okay, so that is how we add stuff, right? So we can manipulate them in any way we want, and that is the resulting vector, purple. And if we pick subtraction, that is how we subtract, I mean, right? So it is a vector that shows us how do we move from this point to this point. And well, but given our convention that all vectors have to start at the origin, our result is this vector, right? It starts from the origin, but it is obtained by a parallel transfer of this dotted vector. Okay? All right?
Yeah. Everything's clear.
Okay.
Clear.
So,
Thank you.
Back to vector spaces. So we have defined how to add vectors and how to multiply them by scalar. And now we can say that vector space is it is a set, and Rn is a vector space with two operations: vector addition and multiplication by a scalar. All good? All good. Let's see how it can look to any curious observer. Okay, we say that we have an addition, and it's commutative operation, which means doesn't really matter if you add v to w or otherwise, right? The result is the same because we arrive at the same point. The operation is associative, which means that brackets really do not matter. We arrive at the same point, no matter what, right? We can do those steps first or some other. We arrive at the same point, no matter what. There is a neutral element, which is a zero vector. You add it, nothing happens. And there is an inverse element. You add it, and you arrive at a zero vector, right? So when it comes to multiplication by scalar, what do we have? Again, we can pick any number value and see that the order in which we do multiplication does not matter. We arrive at the same vector anyways, right? First we multiply by 2, then by 1.5. The result is the same. Again, there exists natural element. 1, we multiply by 1, nothing changes. And distribution works as well. Like this kind of distribution, right? So if we multiply by 2, we arrive at this point. But if we go the other way and first multiply by 2, then add, we have the same result. And another distributivity, which again shows that no matter what we do, we arrive at the same place, right? So this plane, this R2, is clearly a vector space. And now we have a clear and I hope understandable and memorable geometric interpretation for that. Axioms and properties we have listed formally before. Okay. Okay, we said that we do not necessarily have to think about vector spaces in terms of arrows and stuff like that. For example, if we take some polynomials of a degree less than n, or in this case of degree 3, right? So the x to the third is the biggest power we have. We can treat them as vectors. Why? Can we add them? Well, yeah, we can add them. We just add the coefficients for the x and to the same power, right? And we can multiply them by a number. How? Well, we just multiply every member, right? Everything there is by the same number lambda. Okay? So it means that the set of polynomials is actually a vector space, and we can argue that it is, as I said, isomorphic to some Rn, right? So it's basically, since it satisfies all the operation, it is a vector space, and it is isomorphic to Rn. So this stuff has how many coordinates? 4 coordinates, which means that it is isomorphic to R to the fourth, or R4 for short, right? So it doesn't really matter to us if we speak about one or the other. They are likely the same structure with some notational differences, but essentially we can calculate and make and solve everything just as fine, being confined within the first structure or within the second. Okay, is that clear?
Yeah, yeah.
For the other examples, why vectors are so useful, it is because anything that consists of ordered stuff, ordered list of stuff, is a vector. For example, a simple word in English or any other language can be considered a vector. Why? Because it has letters, and letters go in some order. Any color can have its special code. For example, using the RGB palette, right? It has its coordinates, so it can be treated as a vector. And most of the stuff that we encounter, well, at least in physics, can be treated as a vector or something very close to it. So that is why vectors are so useful, because, well, it's actually possible, but quite challenging to come up with something that cannot be described by an ordered list of numbers or some stuff. Okay, another concept that will make our discussion a bit more technical, but more geometrical as well, is called an inner product. We begin with a formal definition and say that an inner product, what it is? It is a function that takes two vectors and outputs a number. But that is not enough. It has to satisfy some properties. First of all, it has to be symmetric, which means the order does not matter, right? So another product between two vectors is the same number, no matter in which order you put them. It has to be what is called positive definite whenever at least one of vectors isn't zero, the inner product with itself cannot be zero. And it has to be bilinear. We will talk about that later. But bilinearity means that it has to be linear for each of the arguments. We have not properly introduced the concept of linearity, and we will come back to that later. But for now, it's just the definition. So why we need this sort of function? Perhaps you're familiar with what is called dot product, which is a particular type of inner product, and how it is defined. It is defined as a sum One may say that it is a weighted sum. So you take two vectors, you multiply the first coordinate by the first from the first vector by the first coordinate from the second vector, then you add the product of second coordinates, and so on, or write it like that with a big sum notation, and well, you get your answer, right? So for example, there are two vectors, we multiply first by first, second by second, and add everything together and get the result. Why it is called a dot product? Well, a few reasons for that. First of all, that sometimes we use dot to show that it is a dot product, but we can use this rectangular brackets as well. And well, at least to my preference, I try to use brackets instead of a dot, but well, that's just up to you. And the other possible reason is because the result is a number, right? And what is a number? A number, simple real number, can be represented by a dot on a number line. So there are two reasons why it's called a dot product. A vector space which has an inner product is called, unsurprisingly, an inner product space. And why it is cool? Because finally we can properly define length and angles there. And if our inner product is a dot product, our space is called Euclidean vector space. And all the glorious Euclidean geometry that we are familiar with can happen there. So, but you should also keep in mind that there are many inner products which are different from dot product. Basically, in some way, we reverse engineer the structures that we are accustomed to from the high school, right? So we're accustomed to using coordinate planes and all that, and triangles, and we know that we have angles, and we can use rulers to measure length, and we never really think about why is that. Well, because we'll learn that, right? Because it's something natural, because, well, all the things that surround us, they have length and, well, angles as well. But taking stuff for granted is not a good approach in math, so we need to properly define that. And finally, the last idea that we'll need and that we have briefly touched upon is norms. So norm is it's basically length. There are, of course, distinctions, but we will not need them. So a norm on a vector space is again a function that takes a vector and outputs a number, right? It can be written with these vertical lines or double vertical lines or just single pair of vertical lines. We have a vector, we put it in our box, and it outputs a number. But again, it has to satisfy some properties. For example, it has to be absolutely homogeneous, which means that if we multiply a vector by some lambda, we can pull it out, right, and multiply by the modulus of lambda. It should be the same. It again has to be positive definite, which means that whenever our vector is not of zero length, its length is not zero, and its length cannot be negative, right? Well, because, that is something that we should expect from a length, because, well, we cannot define what a negative length is. We can use minus and negative quantities when we speak about orientation. For example, we'll be speaking not today, but the time will come, hopefully, when we will speak about determinants, and we will say that we have such ideas as a signed distance or signed area or signed volume, which means signed that we have a sign, and it refers to orientation in space. But the length itself cannot be negative. At least we do not want that to be, so we define a norm to not be negative. And finally, it has to satisfy that triangle inequality, which means that the modulus of sum is less or equal to the sum of modules. Why that works? Imagine that at least x or y is negative, right? In that case, you can see that the right sum will be greater than what we have on the left. Okay. Clear so far?
Yeah, yeah.
Okay. Examples of norms that we will be using. Basically, all stuff that we'll need is an example of what is called an LP norm. Meet so-called L01 norm. What is that? You just add the modulus of any, take the modulus of a first coordinate, add the modulus of the second coordinate, and so on. For example, if we have vector 1, 2, 3, we add 1 plus 2 plus 3. Okay? If we have a vector 1, 0, we add 1, 0, and all that. Okay? It is why it is called a Manhattan norm, or sometimes taxi cab norm, because it represents, looks like the grid, the road grid of New York City, and how cabs move there, because, well, they move like on a grid, like with a sharp 90 degrees turn. So all the points, all the vectors that have the same length, 1, here are depicted in this, well, by the red color, right? So this is how we can assign a norm to a vector this way. If we go a step further and say, okay, now we have L2, and we add the squares and take the square number. So doesn't that ring a bell? Doesn't you remind you something? And of course, because it is a Pythagorean theorem, right? So that is how we usually define the length. And not much of a surprise, here all the dots, all the vectors that have the norm 1, they lie on the circle of a radius 1. Well, Pythagorean theorem works in any number of dimensions, in 2 dimensions, in 3 dimensions, so perhaps it is the easiest idea, but it's basically an Euclidean distance. Again, we perhaps had been using that for a long time, for as long as we can remember ourselves using any math, and did not think that it is some some form of LP norm or something, but it's just one of many. Okay? In general, NLP norm is defined that way. We have a modulus of some coordinate, we take it to the power p, we add all of them, and we take root to the pth power of all that. So L1 is Manhattan norm, or just L1. L2 is Euclidean norm, well, the default norm we'll use. That's why usually we do not write the index 2. Right? Because, well, it's assumed that it is a default. But there are some L infinity norm, which is basically what we do. We take the maximum value. For example, for this vector, we take what is the maximum? It's 3. Here it is 1. Here it is like 1 again, right? Because we care about the modulus of -1. You may ask, why do we need such a weird way to define a norm? Because when we deal with something, we care about either how long it is by itself, but usually we care about how far it is from something else. Coming to our examples, if we have 2 colors and we use RGB palettes, so they have 3 coordinates, right? We have one color and a second color. And we need to answer how much is one color far, how far it, right? What's the distance apart between them from the other color? And we need a way to define, so how do we speak about the distance for a color? Perhaps we can use a simple norm, Euclidean norm, or some other norm, or we have 2 words. And we're trying to program some linguistic model, very simple, and we need it to tell us how good is our prediction, so we can train our model to be better, right? So we need a way to define the distance between 2 words, 2 vectors. And well, etc., stuff like that. We can imagine any distance we want as long as satisfies the axioms we have listed. We can use it as a distance and try to make something closer to something else. Generally, a norm is induced by any inner product. For example, if we have x, it's a norm. Just we take an inner product and just take a square root of that. For example, a dot product induces a Euclidean norm. But not every norm is induced by an inner product. For example, Manhattan norm, or L01, is not induced by an inner product. Not that it's that much important, but still a cool thing to remember. Finally, for inner product vector space, the induced norm will always satisfy this inequality, which is called Cauchy-Schwarz inequality, and it is one of the few incredibly widely used inequalities, and I don't know, a great part of any proofs or any algorithms or practical approaches, they rely upon this inequality, right? So it's true for Euclidean norm, for any norm. And a norm is basically a distance between two vectors. So if we have to calculate the distance between them, we just say it is the norm of what? Of their difference. Well, right? We subtract one from the other and find the norm. And since the norm is induced by an inner product, we just take an inner product of vector with itself and take the square root. For a dot product case, we get Euclidean distance. Okay.
Yeah.
To avoid getting lost, we summarize everything once again. There are lots of spaces and vector spaces in math. Generally, well, it is not the most general, but quite general for our purposes. Type of spaces is called the metric spaces. Those are the spaces that has distance. Something, well, a function that we call a metric. So we can take this function, take 2 points, input them, and this function will tell us what is the distance between those points. Okay? Next, we have normed spaces. Normed spaces have norms the way that we have described them, right? Then we have inner product spaces, which not only have length, but they have angles as well. And finally, if our inner product space is a dot product, we arrive at a familiar Rn Euclidean space. But we need to remember that it is just a tiny, tiny fraction, tiny, tiny subset of all the vector spaces imaginable. And despite they're used for most of the practical needs and calculations, there are many other vector spaces which we can move to if we relax some assumptions, right? Either we consider some inner products different from dot product, or we forget about inner products at all, and stuff like that. Okay, so like a roadmap, we're here. We so far care only about this much of a variety for vector spaces. Okay, is that fine?
It is.
So far, okay. Again, speaking about angles and orthogonality, and speaking about dot product or scalar product in details, what can we say? Let's watch another animation. Okay, we have two vectors. They have coordinates. And we have two, even three angles, right? These angles, alpha is the angle for vector v, and the x-axis b, well, for another vector. And theta is an angle between them, okay? Okay, what we can say? we will say we want to find this angle theta. How do we do that? We take angle alpha and subtract beta, right? As we remember, hopefully from school, there is a cool trick identity, which we can use and replace theta by this difference, right? We expand, and what do we get? We have to multiply the cosines plus multiply the sine of alpha and beta. So given that all that stuff has coordinates, how do we define what is a cosine? Cosine is we take a side opposite, or in case of cosine, adjacent to our angle, and divide it by hypotenuse, right? And we do the same for beta. So we express them, the same we do for sine, and put them in our identity. We have something following, pull out this denominator, and we have our final result, which tells us that this is a scalar or dot product. So it can be obtained in two ways. First, as we have demonstrated before, we multiply every coordinate by every coordinate, first by first, second by second, and add them together, right? Or we can do stuff the other way. We take the modulus or the norm of the first vector, multiplied by the norm of the second, and multiply by the cosine of the angle between them. Both of these approaches arrive at the same result. Okay?
And it works for any inner product vector space, not only for the Euclidean, right?
It is the feature of a dot product. So dot product works for every... Dot product is a particular kind of inner product. There are many, many other inner products.
Got it.
But we care about dot product. Dot product works in any Rn. So 2 dimensions, 3 dimensions, 10 dimensions. Actually, in any finite number of dimensions. And when I tell that, people usually ask, so why do you speak about a finite number of dimensions? Can there be infinite number of dimensions? And yes, it can, but hopefully we will not encounter it in any way, because when we deal with infinite number of dimensions and with infinite dimensional vector spaces, we can come and intrude to the reality of a functional analysis where much of a convenience breaks, right? And we cannot simply do the operations we do now with such elegance. But that will be not our case. Okay, so what is the visual meaning behind that? It means that we can calculate a dot product. For example, if two vectors are perpendicular, or as we might prefer to say to sound cool, orthogonal, it means that what will be dot product between them? It will be 0, right? Why? Because we multiply by the cosine of the angle. If the angle is 90 degrees, what is the cosine of 90 degrees? It is 0. So the result is 0, right? And generally, it can show us the orientation. So if it is negative, well, the angle is greater than 90 degrees. Okay? The same goes for 3 dimensions. Let us see. We have one vector, we have another, and we just measure a dot product between them. Here, briefly, they were orthogonal, and now they are not. All right? Okay, you had some questions, I heard. Or some comments, maybe?
Yeah, I have one question, if you don't mind. So is there is a geometrical interpretation of the dot product?
Yeah, you're looking at that right now.
So it's just like a projection of one vector to another, on another vector, kind of.
It can be, and it can be used, and you actually guessed the contents of our next slides. it can be used to calculate and derive the orthogonal projection. But well, all the geometry you need actually is neatly summarized here, right? We have one length, we have a second length, and we have a cosine. That's all the geometry you need. And as you have noted, you can use that to calculate projections. You can use that to determine angles. You can use that to do a lot of stuff. But in the practice, one of the most useful features is to tell if two vectors are orthogonal, or to build a vector that is orthogonal to what we are considering, right? Because say you have a vector or a plane, or okay, for now, let's say you have a simple vector and you go like, okay, I need a vector that will be orthogonal to my vector. What do I know? I know that this vector, if we take a dot product, will have 0, right? So I can pick the coordinates that will satisfy my equation. And that's how I arrive at the, well, particular vector or a family of vectors, which obviously lie on the same line. If we, well, speak about orthogonality, right? So the whole line will be orthogonal.
Okay, got it. Thank you.
You're welcome. Okay, so I do not think that we have to stop here for long. You can, I'll show you, I'll send you the presentation. You can look at it for yourself. It, like any inner product, it satisfies the Cauchy-Schwarz inequality. You can use that. That is slightly, let me put all the calculations here. It is slightly more interesting because, not because it contains some numerical examples, which are awful, and I have yet to meet anyone who does not fail when he tries to compute those examples. Even, well, the hardest part is using the multiplication table. When someone multiplies 8 by 3, people always get 36 or 22 or something else. So what is, and in real life, you are very unlikely to multiply anything by hand. You will use software, right? But what is interesting here? An interesting part is that we can use the product to answer the question, what is an angle between two vectors, right? And we say, okay, oh, since that product has cosine in it, then to determine what is the angle, we have to take arc cosine of this expression and all that. But apart from the calculation side, why is it interesting? Because it lets us define what an angle is. So from the school, we might recall the two most popular, most general approaches to determine an angle. First, we say an angle is something that we can measure, right? And we can measure it in degrees. For example, we have an angle for 40 degrees, or 90 degrees, or whatever degrees we want. That's the first approach. The second is say, okay, going. Using the same logic, we can identify an angle through using radians and say that an angle refers to some part of unit circle, right? And it is the second way to identify, and then we use not degrees, but we use radians. And radians is basically how many lengths of a radius we have. So the maximum angle will be 2 pi, because the unit circle, its length is 2 pi, right? But here we encounter yet another way. And we say an angle is just something, well, it is this expression. And we are able to define that only because we have an inner product. So if we imagine the most general inner vector space without inner product, we cannot define what an angle is because it does not have angles. So you see the pattern. We have something very general, and all the theorems, all the stuff that we can prove in a very, very, very general case, they hold for all the vector spaces, right? But as soon as we need to get hold of some precise calculations, and be able to actually, well, compute something and be a successful, well-respected and well-compensated engineer, we need to go deeper and deeper and enrich our structures with more and more stuff like norms, like angles, length, and more and more. Okay, so we lose the generality, but we we derive some use from that, because being able to predict something, calculate something, and solve something. And otherwise, when we go up and forget about all the details, we become way more cooler, we become better at pure math, but we not necessarily acquire any more competence in computing. So in case of inner products, we can finally tell what is an angle. An angle is this stuff, and we can be very proud of ourselves. Okay, as we said, two vectors are orthogonal if their dot product is 0, and vice versa. For example, these vectors, they are not orthogonal, but these vectors are orthogonal. Okay? In case both vectors not only orthogonal, but they are of unit length, we say that they are orthonormal, which means that they are orthogonal and they are of length 1. But that's just a convention. If we are too lazy to say that they are orthogonal and of length 1. Okay? Again, no need to stop here in many details. I'll just show you a GeoGebra link, but as you have noticed before, we can use dot product to derive orthogonal projection. And to be more illustrative with that, we can use that, well, in many dimensions, but I'll show you that in 3 dimensions. No, that's not. That's okay. So we have two vectors, right? V and U. And we can use it to derive the orthogonal projection, which is norm of U. So which is a unit vector in the direction of U times cosine theta. So theta is an angle between these two vectors, and we just do that to derive, to come up with orthogonal projection. Okay? And you can play with it however you like. Well, I have played too much here. Okay, we can move V, for example, and get the same result. And here you see all the calculations for that. Okay?
Okay.
So all the familiar geometry becomes actually based on something right now, except for the fact that, well, here are lengths. Well, because we see that there are length and here are angles, and let us see why Euclidean geometry is so good. Now we actually can answer why that any of that works. Our final step today would be planes and hyperplanes, which is basically planes, but in many dimensions. Well, usually when you see this part hyper in math, it means that it's something usual, but in unusual dimensions. So we can have hyperlines, we can have hypercubes, which means it is a cube, but it's not an unusual cube, lives in dimension 3. But what if we speak about a cube that lives in dimension 5 or 10 or some other dimension we can think of? What? Well, then we say, okay, it's a hypercube or hypersphere or stuff like that. Being boring, we can say that a hyperplane in Rn is something that described by this equation. It has n variables plus some free variable which does not depend on n. And so this is our equation, and that means that the dimension of our hyperplane is n-1, so it's one less than the dimension of the space. For example, a hyperplane in R3 will have the dimension 2. A hyperplane in R10 will have the dimension 9. And, well, you get the drift. A hyperplane in dimension 2 will have dimension 1. Okay? But since we are cool and we know how to use dot product now, we can say that we can use more compact notation, basically via dot product. So we can just take one vector, dot product it with another vector, plus b. So it is the same. Okay?
Okay.
For example, as we have said, a hyperplane in R2 is a line. A hyperplane in R3 is just a usual plane, like a piece of paper. And, well, so on. Okay? So, needing a more visual approach, we can arrive with the following clarification. That we can say that this vector W, it defines the hyperplane in which way? We say that V is a normal vector. Normal means it is orthogonal to every vector that lives on our hyperplane. And in that way, if we pick some point, we can say that we can derive a normal vector going through this point such that every vector that lives on a plane is orthogonal to our normal vector, or vice versa, that our normal vector is orthogonal to every vector that lives on this space, on this plane, well, on this plane or space. Sometimes planes and hyperplanes can be vector spaces if they pass through the origin, according to our convention. Yeah, so it is even better way to define that and arrive to what is called the normal equation of a plane. Let us arrive at that. Okay, we'll start very slowly and try to speed up as we go. First thing first, what can we say? We can say that a plane, if we stay in R3, a plane P can be defined through a plane that passes and goes through a point P0. How it can be defined? Let's think of all the ways we can do that. Well, we can imagine that if we have an initial point, we can have two other points, right? And that is enough to define a plane, right? Because, well, we can draw that only, only in one way imaginable, right? So necessarily a plane that passes through all these points, it will be some plane of interest. Okay? Agree on that?
Yeah.
The next thing, next best thing, we can say, okay, consider we have two vectors that somehow emerge from P0. Then we can still use it to draw the plane, right? And we can argue that every point there is can be obtained by adding these two vectors. Here we're not being very formal because previously we have arrived at the convention that all vectors emerge from the origin, but, well, it's kind of like we can do that, right? If we forget that for a moment. But I hope it makes sense visually. Okay? Still the same plane, as you can see. But we can say that a hyperplane NR3 can also be defined by the normal form or normal equation, like that, using dot product. And here N0 will be the previously introduced normal vector. P0 will be a point which this plane passes through, and x1 or x2, x3, any x will be a point on this plane, right? So any point we pick, if we draw a vector, it will be orthogonal to our normal vector. Okay? And vice versa, our normal vector will be orthogonal to any vector we pick on this plane. Okay? All right.
Yeah.
Okay. Going a step further, we can imagine a line for a moment and say that a line in R3 can be defined in many ways, but say we're interested in one particular way. We want to define it using two vectors. The first vector, well, is a starting vector, sometimes it's called a radius vector, and the second vector is called a directional or direction vector. So the first vector basically tells us where do we start. So we start here, for example. And the second vector tells that in which direction we have to move. That's why we scale it by t, because we can move any number of steps in that direction, right? So we have our starting vector and our direction vector. And that is where we arrive, because if we add r0 plus tv, according to vector addition, as we introduced it before, we arrive somewhere here, right? If we pick different values for t, we get all the points that belong to this line, okay? But as we have said before, the line is actually a hyperplane as well. But it is a hyperplane if it is embedded in a space R2, right? So it too has to have a normal form or normal equation, right? How do we arrive at that? Now we consider a plane itself. We have a point through which our line passes, and we draw a normal vector, and all the points, all the vectors that lie on this line, they are orthogonal to our normal vector. By the way, I have to say that sometimes some authors require the normal vector to be of unit length, but not all of them do that. And it's not like, well, it's really important, because if you have a vector that is not of unit length, you can always make it, scale it down or scale up to make it unit length using dot product, by the way. So a hyperplane has the same normal equation, normal form for any Rn, right? And that's very cool, because it has a very cool looking compact equation. We just need a point through which our hyperplane passes. We need our normal orthogonal vector, and our solution, our x's will be all the points on the hyperplane. So, for example, if you have if you're given a point on a hyperplane and some through which the plane passes, and you have some other point, then what you can do, you can draw a vector between them, and you can, by substitution and solving an equation, you can find a normal vector. And that way you can plug it into equation, and suddenly you have the equation for all the points on the hyperplane, right? When it comes to machine learning, how can we use that? We can say that we deal with linear classifiers. And what does it really mean? It just means that we have some points, for example, on a plane, and we want to binary classify them, which means we just draw a line between them, and all the objects that are above this line belong to the class +1, or whatever we might call it, and all the objects that are lower, they belong to the class -1. And we can write the equations for both of those cases. And obviously, well, that extrapolates well to dimensions more than 2, 3. That works for any n dimensions. It is one of the basic and yet quite efficient ways to classify and distinguish points from one another. So, to sum up what we have done today, we introduced some core basic objects. We have talked extensively about vectors, how they are organized in vector spaces. Those vector spaces have length or norms. They have inner products, which allows us to define angles, and, well, norms allow us to define distances and all that. Through being mathematically rigorous, we can define distances without defining norms, but that is not what we're interested in. And we spiced things up with a bit of geometry and said that most of the operations we will be talking about have a nice geometrical interpretation. For example, we have projections, which as well quite orthogonal projections. And by the way, projections are widely used in all the practical math because, well, sometimes it is way more convenient not to deal with the data points themselves, but first we need to project them somewhere onto some line or onto some plane, onto some hyperplane, and to make the calculations easier, and we need to project them in such a way that preserves much of the needed information. So we lose not as much to make, well, the operation pointless. We introduced hyperplanes, which are like normal planes, but in dimensions, any number of dimensions. And we said that the most compact and elegant way to introduce hyperplanes is to use normal equations for hyperplanes, and in that way we need to define a normal vector. And a normal vector is well, it's basically a vector that is orthogonal to each vector that lies on this hyperplane. In some way, well, it is not in some way, but it's very, very much related to tangent spaces and tangent lines. If you think of it and you have some smooth object, you can zoom in on it, and locally it looks like a plane, right? If you zoom in enough. And on this plane, you can build vectors and define a normal vector, and it will change when you travel along the object, and that is how much of differential geometry is derived. Okay, and as the final slide, I have the links I been using today, in case you want to play with them by yourself, but be warned that some of them contain few Russian words. I hope that does not mess you up. So that is all. I will be happy to answer all your questions, perhaps not only related to this lecture, but to the whole field of linear algebra, as much as I know of it.
Daniel, hi, thanks so much for the class. Quick question here. Is there any possibility, maybe not for this class, but for the next class, to have some examples from, I don't know, the previous year exams on this specific topic? So we can see how this theory can be applied to what might be needed in the exam.
Yeah, I guess you should address those who manage the course. Usually they add us, they make a common chat, follow us, and they can provide you with examples and assignments and all that, because, well, obviously we have all the tasks and exams and tests and all the stuff. So
Yeah, no,
well,
no, no. I mean, specifically, so for example, today we went through vectors, like matrix, etc.
yeah.
If you have, I don't know, in your chest somewhere the examples of and tasks for this particular topic, this will be helpful to see like the real things.
Okay, I'll think of it. The more we'll travel along the way, the more examples will naturally have how matrices are, I don't know, you're used to solve equations or derive or change coordinates or derive something like that. I'll think if I can provide more. Well, from today, what we have as practical applications is and which what will be needed in exams is to add vectors, scale vectors, and do some stuff with inner products and define the norm and find the norms over vectors. That's basically it. That's most of it.
Thank you.
Thank you. Question?
I don't have a question. I wanted to thank you. The lecture was really great, and the visualization are super cool too.
Thank you. Nice to hear that, because we have spent many times not on this particular animations, but in the upcoming lectures we will have a very that may be considered as a trailer or something like that. But we'll have an extensive videos that will formally drive how do we change basis when we switch from one vector space to another vector space, and why actually a matrix understood properly is just a collection of instructions of coefficients that are required to transfer from one vector space to another. And I have never encountered any clear explanation for that in the books I've read. The author says, well, the first coordinate transforms like that, and then he puts many dots. Well, you get the picture, but I never actually got it. So we had to soften some, so you won't have to, and I hope you will enjoy that. But yeah, visual illustrations make everything. I have not met any case where seeing how something moves does not aid your understanding. Perhaps if you're very, very smart, or if you did not have a personal life or something like that when you were a kid. Well, okay, maybe you have developed the imagination needed to avoid all the illustrations, but those people are rare and quite hard to find.
Hello, Daniel. Thank you. Thank you very much for the lecture. I was not able to be in the first 5 minutes, so just wanted to make sure something that people were speaking on the chat. There are going to be one lecture. There's going to be one lecture per week, right? For the next 8 weeks. And when are the seminars going to take place for the practical exercises?
Since I'm not the one who will be handle the seminars, ask the managers, organizers, as I'm not aware. Well, it has to happen once a week as well, but I'm not sure what is the day. I can only speak of myself that we will meet on Thursdays every week from now on. So
Okay,
I hope
thank you.
and I hope they'll add us all to the same chat, where we can, chat about the stuff. And in case you're curious, I can send you a lot of links to YouTube, because for years and years, I have been binge watching math videos, and they only get better as the time goes on. And there are many, nice courses on linear algebra, at least on linear algebra as well, and as well as some other stuff. Of course, not every important subject is already covered, but many of them are, and it just makes life incredibly easier for those who have to study it nowadays.
Thank you. Thank you very much, Daniel.
Thank you for your attention. So, anyone else?
Hi, Daniel. Thank you for this, yeah, it's a wonderful lecture. It's really nice to start with this one, And I have just one minor question. So we will get this, the lecture file, right? The presentation.
Right. Right. With all the animations.
Okay,
Right.
great. Thank you. Great.
Thank you.
And one more question, if you don't mind, from my side. Can you recommend any literature specifically, so that I can take a look at that offline as well and maybe go deeper?
Oh, yeah. Well, when they add us to the chat, I'll recommend you. Well, basically, what is the bare minimum is some book on machine learning. That is the bare minimum. What you have to know how this stuff is applied. But speaking of books, popular books on linear algebra, many people like the book by Gilbert Strang. But it is and some people do not like it because it is very heavy on calculations, and some argue that it lacks some more important insights. And but well, there are some books that are like middle ground that both include lots of calculations and geometrical and other concepts. And for those who like pure math, the Holy Grail is the book by Sheldon Axler, and this legendary book is called Linear Algebra Done Right, which contains almost none of the usual calculations, so it is a nightmare for an engineer. It just relies on very, very general definitions, and it avoids coordinates almost completely. So none of the stuff he proves using coordinates. And it's actually cool because as we have said before, coordinates really do not matter. And if you get accustomed to thinking about stuff without coordinates, coordinate-free, you can, expand your power for manipulating those objects almost indefinitely because you are not stuck to certain coordinates. And what makes his book stand apart as well is that he avoids introducing determinants, and he mentions them only at the very, very, very end of this book, and he introduces them as alternating multilinear forms, which does not say a lot. But when he was young, he wrote an essay that was called "Down with Determinants," because determinants traditionally are used in a very cruel manner. They just introduced formally, and they have lots of math and algebraic properties which are not intuitive at all. First of all, they are very extensive and they have lots of indices. They are difficult to write down. And the easiest way for a professor to make students use it is force them to memorize them. But it is incredibly unethical, I guess, to force people to memorize something that does not make sense at all, which is just a sequence of operations, numbers, and all that. So Axler took the third way, and he tried to introduce everything without determinants at all. This will not be the way that we prefer, but we'll try to deal with determinants in the most obvious and illustrative and visually pleasing way imaginable, and say everything about their intrinsic nature and avoid these horrible formulas and derivations as much as we can. So when we answering your question, finally, when they led us to the chat, I'll throw in all the books and recommendations I can think of.
Perfect. Yeah, thank you. I would really appreciate that. Yep. And it's very interesting point regarding determinant. So yeah.
Yeah, it's one of the many. It is really very important concept because not trying to foreshadow anything, but what is a determinant really? It is an assigned volume. So it is just a volume, assigned volume that is made when we take, for example, a cube or something, or a prism that is formed by 3, 4, or some other vectors, and say, okay, it's stuff, it is a stuff, it has a volume, and it is somehow oriented in space, and that is determinant.
Yeah, I've heard about that as well, but like in a little bit different interpretation, that it's just like a scale factor of the linear transformation. If it's like a linear transformation, it shows you how much the like square or volume changes if you apply this transformation.
Yeah, that's well, that is a way to look at that as well. But it says to us, for example, if we take a unit square or unit cube, right, and apply the transformation, so how much its volume really changes. But an important question is, what does it mean if our determinant is 0? And it means that it no longer has its volume because something is linearly dependent. So we lose some necessary information and everything gets squashed down. And yet again, it is, and what Exler is doing and what will be doing, he derives much of that using the properties of functions. For example, what does it mean for a function to be injective or one-to-one, or surjective, or a function onto something, or bijective. And that is very cool because it lets us avoid many of the unnecessary calculations that in any way we will not be doing by hand.
Thank you very much. It's like
Yeah, thank you.